Okay. Um, so maybe a way to do better than Noah, you can go to the study group. There's a segue. Study group led by the Student Learning Center, Monday, Wednesday, 5 to 6. This is the location, 115 Chavez. So we announced this before, but without the location. So there it is. Okay. Okay. So you probably saw, but just if you didn't, I just want to say I made an announcement on BSpace yesterday. Updated the syllabus a little bit. I was not quite following it, so I said what I actually put on the syllabus, what I actually did. And actually the main reason for changing the syllabus at all was that I realized that I made a quiz due on President's Day, where it's a Monday and you won't have section. So I delayed that quiz by a week. So you have a quiz due this coming Monday, but you won't have a quiz due the week after that, which is President's Day. I'll post the second quiz on President's Day, and it'll be due a week after that. Okay, so that's all on BSpace. Okay, I think that's all that. Yes, you also have homework due every week. Okay, so the quizzes are sort of separate from the homeworks. You also have a homework due every week. And like I say, my intention is that the quizzes, you don't spend a lot of time on the quizzes. So I'm hoping that it's not, your experience is not very different on quiz weeks than other weeks. So you only need to get 5 out of 20 on the quiz to get full credit in terms of your grade. People can quiet down a little bit. I feel like even with the microphone, it's pretty loud in here. You can quiet down. Shh. Thank you. Is there a question? I believe I uploaded the new syllabus. Are you looking at it? Does it not look different? Oh, if you go to the syllabus tab, click on the syllabus, you get nothing? Oh, I apologize. I need to repost the syllabus, I guess. I deleted the old one. I guess I didn't put the new one up. Sorry. Okay, so I will. But it's basically what I said, right? There's that change. Okay. Any other questions? Corrections? Okay. So there's just a little bit of chapter 9 that I haven't lectured on yet about change of scale for correlation. So I want to do that today, as well as do the second handout, the handouts on summation and correlation. So where did I put my chalk? Oh. So I'm going to start out just with a little bit of summation, and then I want to talk about change of scale using summation notation. So summation for correlation. So I want to write down the steps I wrote last time for calculating correlation without using summation notation. We have, so to find our by the book, basically, by the way the book does it. Step 1 is to convert x and y to standard units. Step 2 is to take the products of the standard units. And step 3 is to take the average of those products. OK, so that's the way I did it on Tuesday, and the way that the book does it. So the way to do that with summation I'm basically doing the same steps, but I'll just kind of write them down and talk through what's going on. So to find r, if I want to convert x and y to standard units, what does that look like in terms of xi's and averages and stuff like that? So if you want to write this down, maybe leave a little space, or if you want, you can just wait until I'm done and just pay attention to what I'm saying. But yeah, if you're writing it down, leave a little room. X in standard units looks like this, right? So this is x in standard units. Okay. Well, what does y look like in standard units? Sort of the same thing. Okay. So step one is to convert them each to standard units. Step two is to take the products. So I'm sort of doing that here, right? For each value of I, I'm taking a product of some x value. If you want, you can think about this as like heights and weights. That's an example I talked about on Tuesday. It's like xi is the height of an individual person. X bar is the average height of everybody. SD of x is the SD of everybody's heights. This is one person's height in standard units. This is that same person, the ith person's weight in standard units. Okay, so then take the products of those. That's step two. And then take the average of the products. Well, what do we do when we take the average? We add them all up. And we divide by how many there are. So I could divide this whole thing by n. I'm just going to stick a 1 over n in front, just to make it look a little cleaner. Okay? But taking the sum and then divided by n is the last step, taking the average of the products. So you look at this kind of messy summation formula. It really is not different than what the book does. It's just written in the different notation. So again, x in standard units, y in standard units. Step two, take the products. Step three, take the average. So add them all up, divide by how many there are. OK? So that's that, like I say, that summation formula. Any questions about that? OK, so similarly to the standard deviation in the first summation handout, there's another formula that's a little bit easier computationally. I'll talk about that in a minute, but I want to stick with this one for a little bit to talk about change of scale, and I'll kind of refer to this formula for change of scale. So I talked about change of scale for the average, the median, and the standard deviation. For R, I'm basically talking about the same idea. The first is, suppose I add a constant to every value. And I'm going to describe this just to every value of one variable. OK? And second example of, and I'll say what happens in a minute. Let me just make a list of what I'm talking about for change of scale. Multiply each value of one variable by a constant. And I'll divide this into two parts. I'm just going to, save a little space. That constant could be either positive, A positive, or B negative. OK? And there's a third thing that comes up for correlation that doesn't come up for the other two. I mean, it doesn't come up for the other three, I guess, average, median, and standard deviation. So that's all I did for the summary statistics for one variable. For two variables, you might also think about what happens if we interchange the two variables, interchange x and y. OK, so those are all the things that I'll consider to be kind of change of scale. So let's talk about what happens to R. If I add a constant to every value of one variable, what's going to happen? So I'm going to draw. First thing I'll do is I'll just draw a picture of the data I played with a little bit on Tuesday. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So 1, 3, 3, 1, 4, 5, 5, 7, and 7, 4 were the numbers I was playing with before. And I just wanted you to sort of think about correlation as a describing something about this picture. OK? It's describing something about the shape, the tendency that as x gets large, y tends to get large here, positive correlation. I'll draw these lines here I drew last time. This is a line through the average of x and a line through the average of y. And I sort of said that, I guess somewhere in the middle of Tuesday's lecture, if there are values in this upper right quadrant and the lower left quadrant, those values will tend to correspond to a positive correlation. Values in these two quadrants will tend to correspond to a negative correlation. So just to kind of remind you what correlation's about a little bit intuitively. So if we add, like, I don't know, add 3 to all the x values, what's going to happen basically is we're just going to shift this picture over. But the picture itself remains the same. So if you just think about intuitively the correlation is saying something about the picture, adding a constant won't change anything. So adding a constant doesn't change shape of picture. That's intuitively one way to think of R as being unchanged. Okay. A more mathematical way to think about it is to think about what's happening here. So if I increase all the x values by a constant, then if you remember, based on change of scale for the average is affected too, right? The average goes up by that same amount. So if I add 3 to all the x values, x bar, the average of all the x's, also goes up by 3. So the numerator is the same, right? When I calculate the standard units, add 3 to that, the numerator is the same. And if you add a constant to every number on a list, you don't change the SD either, okay? So if I add a constant to everything in a list, or everything for one variable, the numerator here is not going to change, the denominator is not going to change, so the standard units is the same, right? So since standard units is the same, there's no difference when you calculate R overall. And that's actually true for the other variable too, right? I could add a constant to the x's, add a different constant to the y's, still not going to change R. Okay? So let me just write that down here. SU is unchanged. So R is unchanged. It's another way to think about it a little bit more mathematically. Okay, questions about that or comments? Okay. So now let's think about multiplying by a constant. So first of all, think about multiplying by a positive constant. So for example, if I double all the x values. If I double all the x values, well, you might feel like I'm stretching things out. So what effect intuitively you think that might have on the correlation if I double all the x values? I'm kind of shifting everything over. Any thoughts? Any guesses? They could go up. They could go down. So I sort of said correlation measures something about how well the points follow a line. Yeah.
I guess intuitively, one could think that R would go down maybe, because if you are stretching out your values more, I guess there seems like there was more spread, I guess.
OK, so he's suggesting that if you double all the x values, maybe R is going to go down, get closer to 0, because you're sort of spreading things out. Maybe the points are getting farther from a line. Anyone agree, disagree? Any other thoughts? Yeah. So she's saying that the standard deviation will be multiplied by the same value, so maybe that'll cancel out. So she's thinking a little bit more about it and not just thinking, trusting her intuition, I think. So I kind of wanted to ask you that intuitively, because I think your intuition kind of fails here sometimes, intuition about what correlation means. So she's right. The correlation is not going to change. So let's think a little bit about why. One way you can think about it is that if I just double all the values on this axis, I sort of haven't changed the picture. The shape of the picture remains the same. Okay? Now, if you're worried about that, if you feel like, well, stretching it out makes things sort of farther away, correlation intuitively does measure how close the points are to a line, but it's really doing that in standard units. Okay? So when you think about how close the points are to a line in standard units, meaning kind of how many SDs away from the line do the points tend to be, everything's going to cancel back. So again, like if I double the x values, what happens in this calculation is the x values get doubled. That doubles the average. So everything on top is doubled. Standard deviation is also doubled. When I double all the values, the standard deviation gets doubled. So everything cancels, right? So I multiply by a positive constant. Both the numerator and the denominator, everything gets multiplied by that positive constant. So in the end, correlation is unchanged. Okay, so I think that one is a little bit tricky. I think a common thought there is that correlation should maybe tend to get closer to 0 because the points kind of get farther from a line. Well, but in standard units they don't. In terms of the number of SDs away from the line, the shape is basically the same. Okay. Okay. Any questions about that? So again, you can think about that in terms of the SU being unchanged. Okay. And again, actually, I don't have to restrict myself to one variable. I can multiply both variables by a constant. I can multiply them by different constants, as long as the constant's positive. So part B to this is what happens when I multiply by a negative constant. And I'll think about this just as -1. Now, if you want to think about multiplying by -5, well, multiplying by the 5 won't matter because of this. So really, if you want to think about multiplying by a negative constant, it's sort of the same as if you just multiply by one of them by -1. So what do you think will happen to R if I do that? If I multiply all the x values by -1? Yeah. Yeah, it's going to change sign. So I'll say it this way. R is multiplied by -1. If you want to think about what happens in the picture, if I multiply all the x values by -1, I basically flip the picture over to be over here. The 1 gets changed to a -1, the 3 gets changed to -3, and so forth. So it used to be pointing up that way. Now it's going to be like this, and most of the points are going to be in the upper left and lower right. Right? The points there are now like that. Slightly more mathematically, one way you might think about that is that +7 is the biggest x value. When you multiply by -1, it's now -7 is the smallest x value. So if big values for x used to correspond to big values for y, now those values that used to be big for x are the smallest values. So if they used to correspond to big values for y, those values, when they get multiplied, now that it's the small values of x that correspond to big values of y. Okay, so that's sort of intuitively why you might think of it as reversing sign. Okay, if I multiply them both by -1, I reverse sign twice, so I get back to what I started with. I kind of go from here to there, and then from there down to there. So it ends up being whatever I started with. Okay, questions on that? Okay, so the last bit here is if I interchange x and y. Any thoughts? Guesses? Yeah. Turns into its reciprocal. Agree, disagree? Yeah. It won't change. Yeah, so it won't change. So why does it not change? If we interchange x and y, all we're doing essentially is we're doing this in a different order, right? We're just switching the order in which we do the calculation. We still have to calculate x and y in standard units. We take the products. When we take the products, it doesn't matter which order we take the products in. Okay? So this is also going to have r unchanged. Okay, I like the thought of that it might be a reciprocal, but turns out to not be right. Okay, so you can see through all this that it's pretty hard to change r, right? R is pretty stable when we do all these things to it. The only way to change r is this multiplication by a negative constant. That's the only way to change r, and it just multiplies it by -1. So, okay? Questions on any of this? Yeah?
Is it also true if you add the constants to the x variables and then multiply constants to the y variables?
Yeah, so she asks what happens if you multiply, add a constant to the x's, multiply y by a constant. Yeah, you can do as much as you want. In fact, you could like add a constant to the x's and then multiply by a constant, or in the other order, do some things to x, some things to y, do different things, doesn't matter. Nothing you do will change r as far as, you have to do this to every value, every x value, that's the only thing. If you're going to add a constant, it has to be the same constant for every x or every y or both. And same with multiplication. It has to be the same. You have to do the same thing to every value. Okay? Any other questions? Okay, so that's sort of the end of chapter 9. And well, actually, this is the beginning of chapter 9. I skipped over it because I wanted to be able to refer to this equation when I talked about the change of scale. So now I'm done with chapter 9 anyway. And I'll spend most of the rest of the time talking about the handout, and then I'll get back to the book, I think, a little bit at the end. Just kind of preview chapter 10. OK. So here's one formula for the correlation. And like I say, it's basically the same thing as what the book does, just using summation notation. Really, pretty much the only thing that's on the handout is a conversion of this formula to a second formula. So I won't bother with the algebra of that. It's fairly messy, and it's on the handout. But the second formula looks like this. OK, so the way I remember this in English is that this is the average of products. Oops. So you take the products of x and y, and then this first part is the average of those products minus the product of the averages. All that divided by the product of the SDs. And just as a kind of aside, some people were asking, like, well, why can't the correlation be any bigger than 1? Well, let's think about what you mean by a correlation of 1. One way to think about that is that it's sort of as strong a relationship as you can have with another variable. Well, let's suppose that x and y are always the same. OK, so x equals y. So I'll just do a quick calculation. You don't really need to know this, but just as an illustration of this idea. If xi equals yi, always, for all I, what happens in this calculation? So I'm just going to replace all the y's with x's. They're always the same. Then the averages are the same. The SDs are the same. So then we get r equals 1 over n sum I equals 1 to n of xi squared, right? Xi times yi, since they're the same, that's just xi squared. And then I have minus x bar squared. And then the denominator is sdx squared. So what's the numerator? What's the top? It sort of looks familiar, right? It sort of looks like the standard deviation. It is like the standard deviation, but in fact, it's the standard deviation squared, right? The standard deviation looks exactly like that, but with the square root over it. So the top is SD squared, the bottom is SD squared, you get 1. So that's just a little quick, like, just showing you that this is not like a proof or anything, but just an illustration at least that if the x and y values are always the same, then you do get r equals 1. And intuitively, you can't get any better correlation than that. You can't have things any more strongly related than if they're the same, right? So that's that little. It's sort of an aside. It's not really important for you to know that, but I thought I'd just show you since it's pretty quick. OK, any questions on that? OK. So what I wanted to do is, so that second formula, kind of like the SD formula, the second SD formula, it's a little bit easier to calculate using that formula. I don't really care which one you do in general. For some things, this turns out to be much easier. And some of the homework for next week kind of reflects that there's sort of these problems where you're combining two lists of numbers, kind of like last week's homework with standard deviations. So I'll do examples of both those. First of all, I'll just do a simple calculation of correlation using this formula, and then I'll do kind of a longer example where you have to combine things. OK, so I'm going to do this for the same list of numbers that I've been using for a couple of examples. OK. So I did this before. I know that the averages x bar, y bar are both the same, and they're both 4. And I know that SDX equals SDY, and they're both 2, OK, based on previous calculations from previous days. OK, so I know the summary statistics. And what else do I know? So to calculate that formula, I know x bar, I know y bar, I know the SDs, I know n is 5. There are 5 kind of pairs of numbers. All I need to do is calculate the products. OK, so let's do that. Actually, sorry, let me do it this way. Let me just write it here. X, I, y, I. OK? So I'll just multiply these out. So this is like x1 times y1 is 3. x2 times y2, also 3. x3 times y3 is 20. And then 35 and 28. OK? So add them all up. 3 plus 3 is 6, plus 20 is 26. Plus 35 is 61, plus 28 is 89. Yeah. OK? So this is the sum I equals 1 to 5 of xi, yi. Right? So now I'm basically all set. I can just plug in r is equal to 89 over 5. That's the average of the products, minus the product of the averages, 4 times 4, divided by the product of the SDs. Okay, so all that comes out to be 0.45 if you work out the math. All right, so you can see it's quicker, right? The reason it's quicker is I didn't have to deal with converting everything into standard units. I could just take the products immediately and then plug everything in. OK? Questions on that? So like I say, if you have to calculate a correlation that's a little bit faster, although I don't care which one you use. OK. So for another example, this one's going to be pretty long. I want to think about, OK, so I have a list of 5 pairs of numbers. I'd like to add on a list of 5 more pairs of numbers, but I'm not going to tell you what they are. So I have 5 more pairs. And I'll tell you the average and the SD and the correlation for those 5 other pairs. Average of x's is going to be 2. Average of the y's is also going to be 2. And the SDs are both 4. So I sort of just took those numbers and reversed them. And the correlation is minus 0.2. OK? So now what I'm curious about is if I combine both these lists to get 10 pairs of numbers, what are the summary statistics then? So combine lists to get 10 pairs. And find all summary statistics. OK, so I want to find the averages of the x's and the y's, the SDs of the x's and the y's for all 10, and then correlation for all 10 pairs. Okay, any questions on that? Okay, so the first part of the problem is basically doing what I did in the first handout. Finding all the averages and SDs is just that. So I'm going to do it. And actually, you might notice something about the x's and y's is I've at least made life a little bit easier by saying that for this first list, x and y have the same average, x and y have the same SD. Same thing here. X and y have the same average, x and y have the same SD. So because of that, if I find the average of all 10 x's and the SD of all 10 x's, it's the same for the y's. Okay? So there's at least a little bit of symmetry. Okay, so find average of all 10 x's. Oops, x's. So what I mean by that is this, right? Add them all up, divide by 10. So I could get the sum of the first 5 just by doing it, right? I actually know what the numbers are. 1, 3, 4, 5, 7. So I add them up, I get 1 plus 3 is 4, plus 4 is 8, 13, 20. So I know this is what I want. So I know that I could, like I said, I could just literally add them up. It's 20. If I wanted to, I could also think of it as n times x bar, right? X bar itself is the sum divided by 5, right? So this over 5 would be the average, and that's 4. So then if I multiply both sides by 5, I get 20. So I can either do it by math or just literally add them up. For the second list, I don't have that option, right? I don't know what the numbers are, so I can't just add them up, but I can use this little trick. So I'm going to write the second set as I going from 6 to 10, because I want the overall sum to go from like x1, x2, x3, x4, x5, x6, x7, up to x10. So if this is my first 5, then my second list I want to write like this. So I know this is 2. So sum I equals 6 to 10 of xi's. The sum of those last 5 numbers must be 10, right? OK? So then the sum of all of them has to be 30. And you might have just guessed that, right? You have 5 numbers that have an average of 4, 5 numbers that have an average of 2. Throw them all together. The average of all 10 must be right in between. Okay? Sort of think of it as a balancing point. 5 numbers balance at 2, 5 numbers balance at 4. All of them put together better balance at 3. OK? Questions on that? OK, so that's the average of all 10 x's. Same exact thing would give us the average of all 10 y's. I could just replace replace xi with yi, everything I've written here. And I would get the average of all the y's is 3. OK? Questions on average? OK, so that's sort of the easy part. To get the SD, I'm basically doing the summation stuff that I did on the first handout. So to find the SD of all 10 xi's, what I want is this, right? I equals 1 to 10 xi squared over 10 minus 3 squared. 3 is the overall average. So this is what I want. That's the SD of all 10 xi's. And what I need to do to get it is solve for the sum of squares part. Okay? So this is, like I say, the same idea on the first handout. So I can do this one of 2 ways for the first 5. I can actually just square them, add them all up, since I know what the numbers are. So I guess I'll do that. 1 squared plus 3 squared, 1 plus 9 is 10, plus 16 is 26, plus 5 squared is 25. So I have 51 plus 49 is 100. So this is just by calculation. I can just literally do it. Oops, that's squared. Sum of the squared first 5 squared values. So for the second set, I need to do this little, I don't know, sort of trick that I know for second set. The SD is 4, and I know that it's equal to the square root of sum. And again, I'm going to treat this as a sum from 6 to 10, the second set of 5 values. Xi squared over 5 minus the average is 2 squared. OK, so I can solve for the sum of the squares for those. And I'm going to add the sum of the squares of those plus the sum of the squares for the first 5 to give me the sum of the squares for all 10. OK, so when I square both sides, I get 4 squared. 4 squared. Square root goes away. And I'll add that on, I guess. Well, I'll do it as 2 steps, I guess. OK, so this is just getting rid of the square root by squaring both sides. And then I'll throw this over on the other side. 4 squared is 16 plus 4 more is 20. So I get 20 times 5 is the sum I 6 to 10 xi squared, which is 100. OK, so this 20 I'm getting by adding 4 squared, which is 16, plus 2 squared, which is 4. 16 plus 4 is 20. Then multiplied by 5 gives me the thing I want. OK, so they both have the sum of squares of 100. And now I can go back and solve this. So this, actually, let me do it this way. So that, using these 2 calculations, is going to be square root of 200 over 10 minus 3 squared. So 200 over 10 is 20 minus 9, square root of 11. OK? So that's that. Questions on that calculation? So again, this is basically a problem from the first handout so far. OK, questions? OK, so now let's do the kind of new part. I guess I'll erase this. Let me talk about it just for a second. OK, so first of all, what I've done on these 2 boards is to do everything for the x's. And I said before, it's the same for the y's, right? Average of all the y's is also going to be 3. SD of all 10 y values is also going to be square root of 11. Okay, so I know the averages and the SDs of both x and y. So this is the averages of x and y, SDs of x and y. I know n is 10. So basically, I just need this product term, right? I want to find the sum of those products. And I've actually done that for the first 5 already, right? I actually know the value, so I can just literally calculate it. So I get an 89 for the sum of the first 5 products. And then I need to do the same. I need to figure out what that's going to be for the second set of 5 products. So I'm sorry. Let me just to follow the same form. First, I'll write down what I want. OK, so this is average of the products minus the product of the averages. And I know the averages are both 3. And I know the SDs are both 11. Square root of 11. Okay? So this is R, right? This calculation gives me R. And the only thing I don't know is this sum of the products. So I already know. I'll put it over here. Okay? That's by calculation from before, and I could just do it. I know the list of x's and y, so I can just, find that sum of products. So I need the sum of the products for the other set, and I can get that from the correlation for the second list. So the correlation for the second list is minus 0.2. So I can write down for second list, R is minus 0.2, and that is equal to, okay, so I'm again doing the sum from 6 to 10, xi, yi, so that's the average of the products for the second list minus the product of the averages. The averages are both 2, and the SDs are both 4. Okay? So I'm just, like I said, using that same correlation formula for the second list. So I want to solve for this sum of the products term. I have to move things around a lot. Okay, so 4 times 4 on the bottom there is 16. So I get minus 0.2 times 16 equals, well, I guess I'll throw the 2 times 2. That's 4. I'll put that over there as well. So multiplying both sides by 16, and then I'm adding 4. That's going to be 1/5 times sum I equals 6 to 10 of xi, yi. Xi, yi. OK. So then finally, to solve for that, I get this minus 0.2 times 16 is minus 3.2 plus 4, and then times 5 is equal to sum I equals 6 to 10 xi, yi. So this is equal to minus 3.2 plus 4 is minus 0.8 times 4 is minus 4. Plus 4, sorry. Right? Plus 0.8 times 4 is that, I think, right? 4 plus that is plus 0.8 times 5 is 4. OK. So let me just make sure I agree with myself. Yeah. OK, so finally I got the sum of the products for the second group, and I can plug into the original formula. So R is equal to 89 plus 4. That's the sum of the squares for the first 5. This is the sum of the squares for the second 5. That's now out of 10 minus 3 times 3, the averages for the separate groups, and square root of 11 times square root of 11 on the bottom. OK, so this is 93 over 10 is 9.3 minus 9 on top divided by 11 on the bottom. And that comes out to be about 0.03. OK? So that's my overall R for all of it. OK? A lot of algebra. But the idea behind this is roughly the same as the idea for the first handout, that you sort of think about, well, what is it you want? What is it you're trying to calculate here? The thing you want to find the SD, and the thing you don't know is the sum of the squares. Where can you get the sum of the squares? Well, it shows up in the standard deviation formula for each of the lists separately. So you can pull it out of there, solve for it, and then add them together to get the overall sum of squares. Same basic idea here. You write down what you want, and you don't know what the sum of the products is. The sum of the products shows up in the SD, or sorry, shows up in the correlation calculations for each one separately. it turns out for the first list, since we actually know the numbers, we can calculate it directly. But for the second list, we have the sum of the products here. We know everything else, so we can solve for the sum of the products, add them together, and solve. OK? Questions on that? OK, so that's a lot of algebra, but in the end, there's your answer. OK, so let's take a little break. And actually, I'm pretty much done with the handout, so I'll go on to chapter 10. Okay, let's get started again. Okay, so I want to try to move from chapter I don't know, I guess I want to just kind of briefly review everything we've done so far. So for one variable, what do we basically do in each of these chapters? We talked about histograms in chapter 3. So this is a graphical descriptive statistic, picture for data for one variable. Chapter 4, we did summary statistics. So this is, average, median, SD, in particular the average and the SD. And then in chapter 5, we talked about the normal curve. The normal curve is a particular kind of histogram. And you just basically think if histogram is normal, then you can do a bunch of stuff. Normal table, basically. Mostly I'm just talking about using the normal table to do things. You can, convert things into standard units, figure out the percentage of people above, below, whatever, if the histogram is normal. Okay? So I basically want to emphasize that chapters 3 and 4 kind of lay a certain foundation, and then chapter 5 talks about, okay, if we're lucky enough to get a normal curve for our histogram, then we can do a bunch of stuff. So sort of a similarity for two variables. What we've done so far, chapters 8 and 9 really kind of combine two things. Talk about scatter diagrams, which again are a graphical descriptive statistic for two variables, the picture. And we have correlation. So correlation is a summary statistic. Okay? So it's sort of a similar structure in chapters 8 and 9 of starting out by talking about what kind of a picture would we draw and what's a good summary statistic that summarizes something useful about the relationship between two variables. Correlation summarizes like the amount of linear association. It's a measure of the way the book says is the measure of the strength of the linear association, or kind of how close the points are to a line. So chapter 10 and beyond, basically, but just talking about chapter 10 for now, talks about if scatter diagram is what? What's the sort of nice scatter diagram I talked about last time? Just a little bit. Football shaped, good. So if scatter diagram is football shaped, then we could do a bunch of stuff. And the thing that comes up in chapter 10 right now is what's called regression. Okay, so regression is one thing that we can do, and it's sort of nice when the scatter diagram is football shaped. So there really is this nice similarity here that, if the histogram is not normal, if it doesn't look quite like the normal curve, well, if it's close, then your answers from the normal table will be close. If it's far off, if you're dealing with something pretty skewed like income, then your answers might be really quite bad. And we looked at some pictures last time that looked pretty funny looking, nonlinear with outliers, stuff like that. If things are looking like that, then the stuff we're going to do won't be very accurate. But if it looks pretty good, if it looks pretty close to football shaped, a lot of the methods we'll study in chapters 10, 11, 12 will work pretty well. Okay? So we're going kind of studying the ideal situation where it really is football shaped. And I'll talk more about what football shaped means later. But just for now, sort of nice, just like the normal curve is sort of nice. Then there's a bunch of stuff we can do. Okay? So I just wanted to kind of, compare what we did before and what's going on now. And like I say, chapters 11 and 12 do more things with two variables. But for now, we're just going to talk about regression for today's lecture and most of Tuesday's lecture. I think I'll actually have time to get into chapter 11 a little bit on Tuesday also. OK. So what is regression? Well, regression is basically guessing or predicting a y value based on an x value. And I'll refer to this actually as the regression method. And I'll say it attempts to. So this is like guessing someone's weight based on their height, OK? So how well regression works depends on a lot of stuff. One thing it depends on is that your scatter diagram looks reasonably football-shaped. And let's just think for a moment about what qualities or features would a smart prediction method have? Well, if my predictions tend to be really far off, like if someone is 5'3" and I predict that they weigh 300 pounds, that's probably not a very good prediction. Well, why isn't it a good prediction? It's far off from the center. So what a good prediction would do is try to find the average y value corresponding to whatever x value you're talking about. So what I'd like to know is, well, what's the average weight for someone that's 5'3", OK? So that's sort of in the back of your head, you might think, OK, that's basically what regression is attempting to do. It's attempting to find the average y value corresponding to an x value. And that's sort of a smart thing to do. OK, so I want to before I get into like actually how to do it, I think I'll have time today to get into how to do it, but I want to kind of just talk a little bit more about this intuitively. So suppose I want to predict foot length. Okay, and so that's going to be my y variable. Okay, I'm going to try to predict foot length, and there are different x variables I might possibly use. Okay, so I might attempt to predict foot length using GPA, for example. OK, so what's the scatter diagram going to look like here? It's going to roughly look like a circle, right? There's presumably not a very strong relationship between GPA and foot length. The correlation is probably close to 0. No particular reason, I don't think, that people with high GPAs should have longer feet or shorter feet. Roughly, everything's about the same regardless of GPA. So correlation, scatter diagram looks about like that. Correlation close to 0. OK. So let's suppose another option is trying to predict foot length based on height. What's that look like probably? Or anyone want to guess what the correlation might be? I don't know the answer, but 0.7, probably somewhat positive, right? Somewhat positive. We'll sort of presume for the sake of argument that it looks roughly football shaped. I think it probably does. And so let's just say R, somewhat positive. OK, maybe, I don't know. Might be 0.6, might be 0.7, something around there. OK, so let's do one more thought. Let's suppose that I know someone's shoe size. So what does that look like? It's probably pretty close to 1. It's not, not quite exactly 1. If you have two people that wear the same size shoes, their feet might be a little bit different in length, right? So, something like this. OK? pretty close to 1. Okay. So let's think about in each of these cases what my prediction of y is going to be. So let's go back to the first one. Now let's say I have someone that's 1 SD above average for GPA. So here's the average. And up there somewhere is someone that's 1 SD above average. Okay. So that means standard units is 1. Good. Just checking. OK, so if you're 1 SD above average in standard units, your value is 1. Just means that you are 1 SD above average. OK, well, what's the predicted foot length going to be? If you have someone that's 1 SD above average for GPA, how long do you think their feet are going to be? Yeah. Yeah, so you might just guess the average of everybody. And I kind of said at the beginning, a sort of intelligent thing to guess would be the average foot length for people just like that person, right? But there's no reason to think that the people that have a GPA 1 SD above average, there's no reason to think that they have long feet or short feet or anything. So you might just guess the average of everybody, okay? So what I'm saying basically there is that out of all these feet, the average is about the same as everybody's average, okay? So this is average. All right. So then I want to think about the last one first. Okay, so average shoe size here. So I'm thinking about, that's the average. And then, again, think about someone who's 1 SD above average. So I'll just say SU equals 1. Someone 1 SD above average. What do we think about their feet? Well, in the picture, again, you sort of imagine all the people that have that shoe size, they have feet between that kind of lower edge of the picture and the upper edge. So we're going to guess this, right? So this is the best guess or prediction. OK? So I'll just say, to kind of talk about regression a little bit, although I'm not going to tell you how to do it yet. What regression is doing is it's attempting to find that point. It's attempting to figure out what the average y value is corresponding to each x value, right? I just want to do it very kind of loosely, intuitively at first. So what do you think that is, that predicted value? What do you think that is in standard units? Maybe slightly below 1 standard unit, OK? Think. Does that seem right? So if the points are actually on a line, then if you're 1 SD above average for shoe size, you'd be 1 SD above average for foot length. Not a prediction. That just is what you would be if all the points are on a line. OK? So this is close to that. All right? So that turns out to be right, that this predicted value in standard units will be close to 1 SD above average. Won't quite be 1 SD above average, but let's just, it's pretty close at least. And like I say, if it actually was, if the correlation were actually 1, then our predicted y would be 1 SD above average. Now let's not worry about why it's not exactly 1 SD above average for a moment. Just accept that it's close, all right? And I think that makes some intuitive sense that at least you should think it should be close. Maybe you think it is. Maybe you think if someone's 1 SD above average here, maybe you think they should also be 1 SD above average here. And that's not too far off at least, okay? But this case is somewhat in between, all right? It's in between these other two cases. And I do want you to sort of get out of this discussion that if you look at someone whose SU equals 1 here, think about these values. The average of these points is not as far above average as you would get here, OK? Now, a lot of people, I think, when they first think about predicting y from x, they think, oh, well, if someone's 1 SD above average for height, they're probably 1 SD above average for their feet, too. It turns out not to be quite true on average. okay? And that is subtle. I don't expect you to see that intuitively yet. I'll lecture a bunch on that on Tuesday, but I want you to at least, recognize that just in terms of going from that picture to this picture, in this picture, with R close to 0, we're going to guess the average of everybody for the person's feet. If you're 1 SD above average for GPA, we're going to guess that you're just average for foot length, okay? Well, let's say that GPA makes a really small difference. Let's say that people with a high GPA just have slightly bigger feet, okay, for some reason, right? So if that were true, then you would no longer guess the average, but I think it would be a little bit strange to suddenly think that if it just makes a little bit of a difference, if GPA and foot length are just a little bit related, I don't think that you would expect that someone 1 SD above average for GPA would suddenly be 1 SD above average for foot length, right? There's just a little relationship. I think you should intuitively think, well, their feet are just a little bit longer on average. It's not suddenly people with GPAs above, 1 SD above average. It's not like suddenly, just because there's a slight correlation, they have feet that are a whole SD above average, okay? Or if their GPAs are like a 4.0, they're like 2 SDs above average or 3 SDs above average. Those people are not walking around with all huge feet, right? If there's just a small correlation, then you should just expect that there's a small increase in foot length as the GPA goes up. Or the predicted foot length is just a little bit higher as the GPA goes up if there's just a weak correlation. So this is, like I say, it's in between. So you should expect that people that are tall in general have longer feet, but it's not a super strong relationship. So in general, the people that are 1 SD above average in foot length, or sorry, 1 SD above average in height, should be predicted to be, they're predicted to have bigger feet on average, but not as big, not a whole standard deviation above. Okay, so let me kind of summarize this. I'll draw a little chart. So let's say for each case, I want to predict y for x 1 SD above average. Okay, so again, that's standard units equals 1. So for the variable, x variable, 3 situations: GPA, height, and shoe size. And the correlation for GPR is close to 0. Maybe it's actually equal to 0. And for height, for shoe size, it's close to 1. And in between. Okay, so somewhat positive, somewhere in between for height. And now, so I want to think about the predicted y value in standard units. So when I say in standard units, I just mean how many SDs above or below average would you predict y to be. So if your GPA, if you're predicting y for someone whose standard units equal to 1 for GPA, the predicted y should be close to 0. Okay? If it's actually 0, if r is actually 0, the predicted value is actually 0. If r is close to 0, just a little bit bigger than 0, then we would predict that y is going to be just a little bit above 0. Okay? For shoe size, predicted y, last one is going to be close to 1. Okay? Shoe size close, r is close to 1, predicted y in standard units close to 1. Height in between. Okay? So this is just kind of an intuitive way of having me lead up to what regression actually tells us to do. So by drawing that chart and kind of talking through it, I'm trying to lead you to think about how we would actually calculate this. Any guesses? If you're 1 SD above average for x, how do you think we're going to figure out what your predicted y value would be? Yeah? That's right. That's maybe a little bit hard to follow. Let me say it a different way. The predicted y value in standard units should be r. Okay? I'm starting with someone who is 1 SD above average. In standard units, they're 1. And all I need to do is multiply that by r, and that's going to tell me the predicted y value in standard units. That's why these two columns are the same, right? Is all that happens when you predict the y value is you take your standard units for x, multiply by r, and that gives you the predicted y value in standard units. Okay. So let me say that more generally. I've talked through it for just 1 SD above average. So in general, the regression method says this. So the regression method, this is for predicting y from x. Step 1, convert x into standard units. Okay? Step 2, multiply by r. Step 3, convert out of standard units. Okay, so these are the steps. And if you think about what's happening here for the second step, after you've multiplied by r, this gives you the predicted y in standard units. Okay? So if I just talk through my example, if I'm talking about someone who's 1 SD above average, when I convert x into standard units, that just gives me 1, right? And then when I multiply that by r, what that's telling me is that the predicted y value in standard units should be r, meaning r SD is above average. And now I need to convert that out of standard units. Okay? So those are the steps for the regression method. I guess I have time for one quick example of it. Actually, instead of doing an example, let me just draw a picture. I'll do an example on Tuesday, but those are the steps. So I want to draw a picture and just give you some highlights of what's going on in this picture. And you can think about this as maybe being, well, let's make this height and weight. OK, so what I said at the beginning, or towards the beginning of all this discussion, is that what regression is trying to do is find the average y value corresponding to each x value. So those points are called the graph of averages. So let's just plot that on here. So what I'm basically saying is that for each x value, consider the y values, take their average. Okay? So I'm trying to draw like basically halfway in between the top and the bottom of my picture. Okay, so that's maybe the point in the middle. If you remember, this one in the very center is called the point of averages. And these other ones are called the graph of averages. So this is average y for each x value. OK? So like for everyone with a different height, if we thought about what their average y values are, we get those points. Now, it turns out if we do the regression method, those points are all going to be on a line. These predicted values are all going to be on a line. So I don't know. I'll talk more about this Tuesday. But roughly, if you want to think about why that's true, when you convert x into standard units, what are you doing? Well, you're subtracting x from every value, and you're dividing by the SD. So you're doing the same thing to every x value. And then multiplying by r. Well, that's sort of multiplying and adding constants. Well, that's exactly what you do when you graph a line, like y equals mx plus b. You're multiplying by x by a constant, adding a constant. So if you think about what's going on here in these steps, don't think too hard about the algebra, but basically what's going on is we're going to get a line out of this. For each x value, once we do this transformation, those points are, that calculation will give us a line. The graph of averages doesn't necessarily have to exactly follow a line. There's no like law written in stone that says that the average weight for everyone that's 5'3" has to be there. For 5'4", it has to be there. For 5'5", it doesn't say this has to be exactly on a line. It might be for some reason, just sort of randomly or whatever, that the 5'4" people are a little bit heavier or a little bit thinner. Okay? So it's possible that these points aren't exactly on a line for the graph of averages. The regression method itself gives you calculations that are on a line, and that's called the regression line. Okay, so regression line is sometimes referred to as a smooth version of the graph of averages. So like I say, there's some pictures of this in your book that show that the graph of averages is not exactly a line, but it's pretty close. And the regression line basically goes pretty much through them. Okay? So if you want to think back to our pictures here, graph of averages here basically looks more or less like a horizontal line. Here, it's like a line like that. And here, all the points are quite close to a line, going more or less straight through the picture. OK? All right, so I wanted to get that picture there and kind of talk about some of the highlights. I'll talk a little bit more about this on next Tuesday and do some calculations. OK? So questions? OK, let me know if you have any questions. You can come up. Have a good weekend.